Hi, mathletes! Today we're going to be launching into quadratics, the math behind vertical motion. We'll explore how gravity, time, and height reveal the power of quadratic equations. So welcome to today's video, Quadratics in Motion. Step right up because you're about to join the circus. Lori, the human cannonball, is relying on your math skills. So today you'll learn how vertical motion can be modeled with quadratic equations. You will use real-world data to make predictions about height and time. And you'll discover how a formula like y equals negative 16x squared plus vx connects physics and algebra. So let's take off and see how far math can go. So about 500 years ago, Galileo discovered the mathematical formula to define vertical motion. He was a pretty smart guy. Vertical motion refers to the movement of an object that is thrown, struck, dropped, or propelled into the air on Earth. Actually, it is on any planet, but the formula is different for other planets. So Galileo found that vertical motion can be modeled by this equation. Y equals negative 16x squared plus vx. Y represents the height of the object and in feet at any time in the problem. X stands for the time in seconds from the moment the object starts moving. And v is the initial velocity, the speed of the object at the start. Negative 16 is the coefficient for the pull of gravity on Earth. So this number would change if you were on a different planet like Mars. So here's the situation. You've got a job with the circus, and you're going to assist Lori, the human cannonball. Lori is going to be shot out of a cannon, and you are going to ignite some fireworks when she reaches her maximum height. Then you're going to play a bit of victory music when she lands. But the only problem is you can't see anything from backstage, and you need to know precisely where she is at each second to do these things. And on the first shot, Lori will be shot from the ground with the initial velocity of 160 feet per second. This would make her equation y equals negative 16x squared plus 160x. Notice that I replaced the v with 160 because v is the velocity. Remember that x is the time in seconds from the moment the object starts moving, and y is the height of the object in feet at any time in the problem. So let's use this equation to calculate where Lori will be after a given number of seconds. So after 1 second, here's my equation, y equals negative 16x squared plus 160x. And so since we're talking about time, we're going to replace each x with 1 for 1 second. Now we're going to do the 1 squared first because we have to think of order of operations, which is 1. Then we will multiply, and again multiply, and then we will add. And it looks like after 1 second, Lori will be 144 feet in the air. Here's what it would be in 2 seconds. She would be at 256 feet. At 6 seconds, she'll be at 384 feet. At 9 seconds, 144 feet. And at 11 seconds, negative 176 feet. What do you see? What do you think? And what do you wonder about these results? You might want to pause the video here and look this over in more detail. Okay, well, let's continue on. I thought that those answers looked a little strange, and you probably did too. So maybe if we look at the big picture, that would help. So we can make a table of values showing the time in seconds and the height in feet of Lori from the time she is shot to the time she lands. So here's my table with time and height. And I just picked some numbers. I did not pick them in order. As you can see, 1, 2, 4, 5, 6, 8, 9, 10, 11. Now, some of those we already calculated from the previous slide, but we didn't do 4 seconds. So at 4 seconds, it's 384 feet. At 5 seconds, it was 400 feet. At 8 seconds, it was 256 feet. And at 10 seconds, 0 feet. So I put those now into my table. So we're going to use this table to answer some questions. So what would Lori's maximum height be? Well, if I'm looking at this table, it looks like the highest that she was 400. So 400 feet. And after how many seconds does she reach this height? Well, it looks like it's going to be 5 seconds. And at what time will she land safely? Well, that would be where the height is at 0. So it looks like it's about right here. So at 10 seconds. Now let's graph our data. I put the table over here to help. So here I am graphing it. I have my title of my graph, relationship between height in feet versus time in seconds. The independent variable, which is my x, is my time in seconds. My dependent variable, or y, right here, is the height in feet. So you can see I plotted my points, and it looks like it makes a bit of a curve. Let's connect those points. Sure enough, it looks like it definitely makes a curve. It's not a straight line at all. Well, we call this shape a parabola when it makes a curve like this. Now let's mark Lori's maximum height, and we'll put a star up there. So let's put the star because that's when you need to be able to play or do the fireworks. And so there it is. So how about her landing time? Let's put a smiley face so that you know when to do the victory music. There it is. Okay, so why do your answers in the table make sense now? Oh, I can see like for 1 second and 9 seconds, it's the same because they're going up and they're going down. Interesting. And the negative, because it would be down here, she already landed. So that's why the answer makes sense for 11 seconds, right? She already landed, so she's not going to go below the earth. Now, Lori thinks she went too far on the first shot since she landed in the elephant enclosure. Whoops. So on the second shot, she decided to use the initial velocity of 120 feet per second. So let's define our variables and write an equation for Lori's second shot. Again, x is the time in seconds from the moment the object starts moving, and y is the height of the object in feet at any time in the problem. So my equation now is y equals negative 16x squared plus 120 now, because I changed the velocity from 160 to 120x. And here's my table, and we'll pick some seconds. This time I picked 1, 2, 4, 5, 6, 7, 8. And we can calculate the height. So for 1 second, it looks like it was 104 feet. 2 seconds, 176 feet. 4 seconds, 224 feet. 5 seconds was 200 feet. 6 seconds is 144 feet. 7 seconds was 56 feet. And 8 seconds is negative 64 feet. Now let's graph this data, but let's graph it on the same as our previous graph. So our previous graph is in red, and our new graph is in purple. There we go. And you can see in the red one with the velocity of 160, this is where Lori reached her maximum height, and this is where Lori landed safely. This is our new one in the purple. So what is Lori's maximum height now? Let's see, in the purple one, it looks like it's right here. And so it looks like it doesn't land specifically at 200 or 250. It's in between about halfway. So I'd say about 225 feet, which means it's a little bit, let's see, if we look at 225 feet, so a little bit over there. And at about how many seconds does Lori reach this height? Well, let's see. It looks like it's in between the 3 and the 4. So it looks like it's going to be about 3.75 because, again, this is 224 feet, and it looks like it was a little bit before that when it was getting bigger, and then it starts to go down. What time does Lori land? Looks like she's landing right in here. So it's somewhere in between the 7 and 8, and it looks like it's about 7.5. So it was hard to tell this looking at the table because none of those numbers matched up. And some of these points were in between our whole numbers. So this is where the graph comes in handy. So at what time is she at 200 feet? 200 feet looks like it was right here. Oh, that was a nice one. That was at 5. And sure enough, it says 5 right here on our table. So where is she after 2 seconds? Well, about 175 feet. We'd say about 175. Actually, it's 176. So if you look at the table, it's going to be more exact than looking at the graph because graph is going to give us an about. So now that you looked at this, how are quadratics similar but also different from linear functions? Think about that. So what did we discover in this video? Well, we discovered that quadratic equations can describe real motion, like someone being launched from a cannon. The shape of the parabola helps us find maximum height and landing time. Changes in initial velocity, v, directly affect the object's path. And math is not just numbers, it's a tool for prediction and understanding the world. If you enjoyed this video, I'd love it if you subscribed or click the like button. And as always, thank you for watching. And also, thank you for helping Lori make it through the act, thanks to your calculations.